Okay, this is part 2 of the lecture on the heart. We're going to start here with the conducting system, and I think it's important for you to recognize that within the heart itself, there really aren't any nerves. What there are cells called conducting cells, which are autorhythmic cells that can control and coordinate the heartbeat. So they act as if they're nerves, but they're actually cardiac muscle cells. The heart ordinarily beats in a synchronized fashion. The atria are going to contract first. As they start to relax, the ventricles then contract. And that contraction of the ventricles then is followed by a pause, a period where the heart can fill with blood before the atria contract again. So you kind of have 3 parts to each heartbeat. You have atrial contraction, that sends the blood to the ventricles. Ventricular contraction, that sends blood out to the arteries. And then this resting period, that is the filling period. So we need these 2 kinds of cells. We need the autorhythmic cells, which are the conducting cells, and then the contractile cells that are actually doing the work of the heart and pushing the blood around. So let's focus our attention on that specialized conducting system. These specialized cells are going to be adapted to sending the electrical signals very quickly and in a particular manner. The term autorhythmicity is important. There are other tissues we'll look at later that are autorhythmic. Auto, remember, means self, which means that if you cut the heart out of the body and you disconnect it from the nerves, it continues to beat. It has its own rhythm. The first part of the conducting system is the sinoatrial node. This is called the pacemaker of the heart because its rate is faster. Its autorhythmic rate is faster than any other parts of the heart. It's going to send signals in 2 ways. It's going to send signals to the atrial wall, the right and left atrium, and tell them to contract. But it's also going to send signals through an internodal pathway to a second node, the atrioventricular node. And the atrioventricular node is going to hold the signal long enough for the atria to finish contracting, and then it's going to send the signal through to the ventricles. And the ventricles receive the signal from the AV node through this particular pathway. The atrioventricular bundle splits at the top of the interventricular septum into a right and left bundle branch. At the apex of the heart, that signal goes out through Purkinje fibers to the outer ventricular walls. So, what makes the SA node the pacemaker? Well, what makes any of these cells autorhythmic is that they gradually depolarize. They do not have a resting membrane potential. So they're continually sort of drifting towards threshold. And you remember that threshold is the point at which an action potential is triggered. So these autorhythmic cells sort of gradually leak in ions until they get to threshold. And in a normal heart, the SA node is going to leak these positive ions faster than any other part. So what happens is that you get this normal sinus rhythm when the SA node depolarizes first, because once it depolarizes, it blasts the signal out to everybody else, and they don't get to reach the signal on their own. The SA node has a natural rate of 60 to 100 action potentials per minute. But in a resting heart, we're going to slow that down through parasympathetic stimulation. Now, I know you all studied the autonomic nervous system last semester, and you know that the sympathetic nervous system is fight or flight, and parasympathetic is resting and digesting. So the parasympathetic continually slows down the heart at rest. And only when you're active do you quit getting parasympathetic stimulation. So if you're sitting down in a chair listening to me talk to you, you have parasympathetic stimulation going down the right and left vagus nerves and continually slowing down your pacemakers. So here, look at the purple. We're kind of looking through the heart as if we had X-ray vision. The SA node is up there near the superior vena cava. The AV node sits right next to the right atrioventricular valve, right in the floor of the right atrium. The AV bundle leads into the interventricular septum, and then there are the right and left bundle branches down to the apex, and then Purkinje fibers up through the outer ventricular walls and even into the papillary muscles. Now, this is a graph of the action potential of the sinoatrial node. And you'll see what we call the pacemaker potential, sort of gradually rising till it gets to threshold. And once it hits threshold, it depolarizes and then it repolarizes. And again, a normal rate is going to give you about 70 or so beats per minute, about 0.8 of a second for 1 beat of the heart. So the SA node it depolarizes, that activates the atria, that spreads the impulse across the atria, which causes atrial contraction. It gets to the AV node after about 100 milliseconds. That's about 1/10 of a second. So remember, our whole heartbeat was 0.8 of a second. The first 1/10 of a second is for atrial contraction. Okay, the signal can be read by an ECG machine, electrocardiogram. You put electrodes on the surface of the skin, one from the left side of the heart to one on the right side of the heart, so you're measuring electrical change as the heart has its activity. And in the ECG tracing, as the SA node activity begins, until the atria get their signal, you're going to have a flat line as shown as the little red short segment in the ECG tracing. But then as the atria start to depolarize, you get what we call the P wave. The P wave takes about 50 milliseconds. And it's followed by atrial contraction. So atrial contraction takes about 100 milliseconds. And after that 100 milliseconds, then the signal gets through the AV bundle and starts to reach the ventricles. And you've got to go down those left and right bundle branches to the Purkinje fibers and out the Purkinje fibers to the ventricular myocardium. By this time, the atria finished contracting, and we're going to start contracting the ventricles. We're going to get a complex wave called the QRS. Now, we're not going to say the Q is one thing, the R is another, and the S is something different. We're just going to combine them into the QRS signals the beginning of ventricular depolarization, and that's going to trigger contraction of the ventricles. And our elapsed time at this point is 175 milliseconds. Remember, that first 100 milliseconds was taken up by the atria. So we have the rest of our QRS, and now the ventricle walls are completely depolarized, and they're going to contract. Now, we're going to stop at this point and talk about some things that can go wrong. Bradycardia means your heart rate's too slow. Tachycardia means it's too fast. If you have an ectopic pacemaker, ectopic kind of means in the wrong place. So if you have some cells that become abnormally excitable, or if your pacemaker cells are damaged in a myocardial infarction, then some other part of the heart can take over as an abnormal and ectopic pacemaker. And it's going to either go too fast or it's going to go too slow if the pacemaker got killed off. But the main thing is it's bypassing the conducting system. It's not following the right pathway, and it's going to lead to irregularities, not just in the timing of the contraction of the heart, but in the sequence. So we use an ECG or EKG, an electrocardiogram, to record the events of the heart. And we know what a normal pattern looks like, a PQRS. So it's not hard to diagnose abnormal patterns. P for depolarization of the atria, QRS for depolarizing the ventricles. And then following that, the T is repolarizing of the ventricles. Now you might notice we don't have repolarizing of the atria in this list, and the reason is the atria repolarize at the same time the ventricles are depolarizing, and you simply can't see the signal. The ventricular signal just kind of swamps out the signal from the atria. So we can do some measurement from here. We have some normal intervals. The normal time between the P and the R, if you measure that, you're getting a measure of the time the atria have to contract. In the QT interval, you have the time it takes for the ventricles to contract. So those are very useful intervals. And this is pretty elaborate, but you've got what we call a 12-lead ECG. And you can tell a lot about a person's heart by doing this. I'm not testing you on that. So here in the upper picture, you can see just sort of a sequence of, it looks like 1, 2, 3, 4 heartbeats. And then in the lower figure at the bottom, you've got, if you see 2 R's, you're looking at 2 beats of the heart. So we can measure the distance from one R to the next R, and that gives us the heart rate. Please study the graph so you know the PR interval, the QRS, the QT, and the ST. Some abnormalities of the heart, let's just go from top to bottom. What you see in the first is that you have an abnormality in how close together the heart rate is. This is premature atrial contraction. Something's excited the atria, and when the atria contract, then the whole heart contracts. Now, if you look at the middle one, paroxysmal atrial tachycardia, notice that what's missing here is any filling period. So look again at the previous picture and notice there's a big gap between a T wave and the next P wave. That's the filling period. So if you look again at this middle picture, there's no time for the heart to fill. So if you have tachycardia, in general, you've got a heart rate that may be so rapid that there's really not that much blood flowing, and you're going to have a patient who is weak and passes out maybe when they're standing up, and their heart rate is just 180 or more. In the lowest figure, you can see nice QRSs, maybe some T's in there, but no distinct P's, and there's just a lot of quivering lines in there. So this is a fibrillation. A fibrillation is a loss of the normal rhythm. If you have ventricular fibrillation, then the heart's not pumping any blood at all, and you wouldn't be probably measuring that on an EKG because you'd be trying to revive your patient. And there you see it at the bottom, ventricular fib. Okay, so again, tachycardia, premature contractions. I'm not going to ask you to diagnose any abnormal ECGs on the test. All right, now we're going to turn our attention to the contractile cells. This, of course, is most of the cardiac muscle tissue. These are the cells that receive the stimulation from Purkinje fibers in the ventricles, although in the atrial wall they're getting radiations from the sinoatrial node. We need to review membrane potentials, resting potentials, and action potentials. So you got to try to remember that from AMP1. You remember that the resting membrane potential is in a nerve cell, it's usually about -70. A little different here. You don't need to worry about that, -80, -90. The point is it's going to be stimulated to contract only when the conducting cells are going to hit it. All right, now we're going to shift gears again, and this is going to seem kind of disconnected, but just quit thinking about that for a minute. Let's talk about how the cells are connected to each other. Cardiac muscle cells have what we call intercalated discs, and these are connections between the adjacent cells of the heart, not just the contractile cells, all the cells of the heart are connected, and they have lots of folds, which gives them a lot of surface area. And they have two kinds of cell junctions along these folds. One is desmosomes, which you should remember from ANP1, help stitch cells together, so it keeps the cells from pulling apart from each other. And then also gap junctions. And gap junctions allow the flow of ions from one cell to the next. It gives direct cell-to-cell communication, and that's how cells, when they're stimulated, will stimulate the neighboring cells, and that propagates the action potentials. So once you stimulate one cell, then through the intercalated discs, which you can see a nice 3D at the bottom portion of this figure, you can see how high the surface area is. You can see that the cells are going to communicate with each other. So here's a close-up showing you the gap junctions and the desmosomes, and it's the gap junctions where the ions can flow through directly from one cell to the next cell. So contractile cells are generally smaller than conducting cells. They do have branches, and their unique feature is those intercalated discs, which you should be able to recognize from a micrograph. All right, so back onto our physiology story. Once these cells get stimulated through their gap junctions, that opens voltage channels for sodium. This depolarizes the cells very rapidly. We're going to get a unique feature in cardiac muscle. It's called a plateau, and you'll see it on the figure and it will make some sense to you. But when depolarization occurs, then that causes an opening of calcium channels. We call these the slow calcium channels. And the calcium channels, when they open, let calcium into the cells, which helps cause them to contract. And then at the end of the plateau period, you're going to have what is just normal repolarization. Potassium channels are going to open. It's going to rush out of the cell and repolarize the cell. Now, the other aspect of the action potential that you need to remember is the refractory period. I'm hoping you remember that the refractory period is the period when the cells are resistant to restimulation. During the first 200 milliseconds or so, you cannot restimulate these cells. They're contracting, they're even starting to relax, and you still can't restimulate them. During the relative refractory period, the last 50 milliseconds or so of the action potential, you could, so if you have strong sympathetic stimulation, you can cause the heart to respond to a new action potential, but it's just more difficult to. So typically you're going to go through that whole refractory period of 250 milliseconds. That refers to what's happening in the ventricle. Something similar happens in the atria, but in the atria it only lasts about 100 milliseconds. So during the refractory period, the heart cannot be re-stimulated, and since you can't re-stimulate it, it's always going to at least partly relax before it can start to contract again. So you always have contraction followed by relaxation, followed by contraction, followed by relaxation. And so you cannot have tetany in the heart. All right, so here's our graph of the action potential. Again, this is a ventricle graph, but an atrial graph would look a lot like it. It would just be 100 milliseconds instead of 300. Period 1 is the period of rapid depolarization. Sodium is entering because the cell was stimulated through its gap junctions that cause the opening of voltage gates for sodium. As it gets up to about plus 30, you get into the plateau. And the plateau is caused by the influx of calcium through slow calcium channels. That's going to last about 200 milliseconds, and then you're going to have repolarization. And remember that the heart is always going to partly relax before it can contract again, because the absolute refractory period goes into the period of repolarization. And you cannot contract it again until it's at least partly repolarized. Okay, contrasting that with what happens in skeletal muscle. So on the left, you have at the top action potential and at the bottom the contraction of skeletal muscle. Notice that the action potential in skeletal muscle is completely over before contraction really gets started. So in blue, you have the absolute refractory period. In pink, you have the relative refractory period. And so the relative refractory period in skeletal muscle is over before contraction peaks. Now, look on the right, and you've drawn out this action potential with the plateau. And again, comparing the blue and the pink, what you see is that in the heart, it starts to relax before the absolute refractory period is over. There's simply no way to cause the heart to go into tetany. Calcium ions are absolutely crucial for two things. They do help depolarize the heart. They give you that action potential plateau, but they also trigger the release of more calcium inside the heart muscle cells. Remember, the sarcoplasmic reticulum stores calcium. So about 20% of calcium in the heart comes from the outside as it's depolarizing, as it's going through the plateau, and 80% is stored inside the muscle. That's very different than in skeletal muscle, where all of the calcium for contraction comes from the sarcoplasmic reticulum. So cardiac muscle tissue is very, very sensitive to extracellular calcium concentrations. If you have too much calcium in your blood, that would be hypercalcemia. It actually makes the heart go into tachycardia, and likewise, if it's too low, the heart can go into bradycardia. Those slow calcium channels are going to close as the cells start to repolarize, and we're going to put the calcium back where it came from, either back into the extracellular fluid or back into the sarcoplasmic reticulum for storage. All right, we're going to stop here, and we'll pick up in part 3 with the energy for cardiac contractions.